In this video, we are going to look specifically at the roots of complex numbers. So there's a few things that we have to pay attention to. First, we have two formulas here that we can use in order to find the roots of complex numbers. The first formula has the complex numbers similar to our standard form idea of complex terms, where here we would have z to the 1 over n. 1 over n represents the root, so n is representing that root term. And then you would have the cosine of this mess of stuff, which is your angle over your root, plus k times 360 over the root, and then obviously plus I sine that same mess of stuff. Now with that, we have to calculate the k term, and your k term is found by doing n minus 1. So remember, n is represented of your root value, so your k term is going to be 1 less than that. The second formula we have more resembles Euler's method, where we have the magnitude of z to the 1 over n. Again, it's the same thing. N is your root. And then we have a form of Euler's idea, where we have the angle plus 2k pi. And what you have to notice here is that the Euler's idea is going to deal with radians, whereas your standard form idea is working more with your degrees. Okay? So what I'm going to do is show you a couple examples. The first example, we are going to look at both formulas used for solving, so that you can see how both of them work. However, most students or people think or reference the Euler's method as more of a shortcut method. There's kind of less involved with it. So let's go ahead and take a look. So the first thing that we have here is we have the square root of find the square root negative square root 3 minus I. So the first thing to note is that right here we have this square root term going on. This is telling you what we're doing. So in this case, we are told that n is equal to 2, and that's because this is square roots. And the second is we're given our reference angle information. So we have negative A, negative B. So we're going to be here in that third quadrant. So the first thing we want to do is find out the information we need. Okay. So we need to know what this entire angle is. So this is the angle that we are looking for. However, to do that, we need to know this piece right here, which we call your reference. So this is the reference angle. We get that by using our terms. So here we've got, this is the negative 3, or square root of 3. This is negative 1. We would use Pythagorean's theorem to find this is your z value here, which we would find to be 2. Once we determine that, we can determine your reference angle. So here we've got, say, the cosine of my angle of reference is going to be negative square root of 3 over 2. So that tells us that your angle of reference is equal to 30 degrees. Okay. You can check it by looking at the other angle, meaning if we take the sine, we would have negative 1 over 2, which we also know to be 30 degrees. So this is that reference angle piece that we have. So to actually find your angle, so our theta, is we have to use our reference rule. So we're in the third quadrant. Third quadrant says we would take the 180 degrees plus your angle of reference, and that is going to give you your angle. So here this is going to be 180 plus my 30 is equal to 210 degrees. So this is the important angle that we were looking for. So we need to start plugging our information in. So first of all, we know your n value. We know your angle. We also know our k value. Your k is equal to n minus 1. So this would be 2 minus 1, which equals 1, but then you have to go backwards all the way down to 0. So then we would also look at 0. So here we're going to evaluate it using two values for k, the 1 and 0. So the first thing we're going to look at is we are going to go ahead and look at k equaling 0. And I'm going to go ahead and use the standard form. So we're going to use z to the 1 over n times cosine of that mess of stuff plus I sine of that mess of stuff. So the first and foremost, or the first thing that I would always do when calculating this, is we need to find out what that stuff is going to be. So that's going to be theta over n plus k times that 360 degrees over n. So my theta value is the 210, n is 2, plus my k. In this case we're using k as 0, so this would be plus 0 times my 360 over 2. Well, when we look here, anything times 0 is 0, so this is going to end up being 105, because the only thing we have is 210 divided by 2. So here my z value is 2, so this is going to be 2 to the 1/2 times cosine of 105 plus I sine of 105. And the other way that we like to look at this is we like to rewrite this. So instead of to the 1/2, we would say the square root of 2 times cosine of 105 plus I sine of 105. And there you have it. Now the other piece we have to look at is what happens when k equals 1. Okay, so let's go ahead and take a look at that here. So we have k equals 1, and in this case I'm going to go ahead and use the Euler's formula, which says the magnitude of my z to the 1 over n, and then e to the I times my stuff, which is theta plus 2k pi all over n. So the first thing we need to do here is we need to input what we know, but then we also need to reduce my stuff. So here this is going to be 2 to the 1/2 e to the I times my stuff. So I need to find out what that stuff is going to be. So here let's take a look at it. I have theta plus 2k pi over n. So let's plug in what we know. My theta is 210 plus 2, my k is 1 times pi, my n is 2. Now if we look at this, I have degrees and radians. So I need to convert 210 degrees into my radians. So to do that, I can use my unit circle, or I can use the rule that says to my conversion rule to get over to radians, pi divided by 180. So in this case, if I use the unit circle, I know that my 210 is going to be the same thing as 7 pi over 6. So I have to plug that in. So it would be 7 pi over 6 plus 2 pi, and the whole thing is over 2. This numerator we need to combine by using common denominators. So this is 7 pi over 6 plus 12 pi over 6. When we add those together, we end up with 19 pi over 6. So here we've got my 19 pi over 6 The whole thing is over 2. Our fraction rule says we're going to keep that top fraction, and we're going to multiply by the reciprocal of the bottom, which is going to turn this into 19 pi over 12. Now we just did a lot of work, but all we did was simplify what went here into these parentheses. So we have to rewrite this. So 2 to the 1/2 is the same as the square root of 2. And then this is e to the 19 pi over 12 I. And this was what we were looking for. So as you can see with this particular root problem, the biggest part of the math is coming from calculating the stuff that goes inside the parentheses here. Alright, let's go ahead and take a look at one more example. And so here this one is solved or done a little bit differently. So we have z to the 4th plus 81i. So the first thing that we have to do here is we have to solve for z to the 4th. So in this case, what we end up getting is that z to the 4th is equal to negative 81i. And off of that, we need to identify a couple things. First of all, my a is equal to 0, and my b is equal to negative 81. So here's a note that we need to keep in mind. Okay. Since a is equal to 0, your theta is going to equal plus or minus pi over 2, dependent on the sine of the b term. Now for us, my sign here is negative. It's negative 81, which means for this problem, my theta is going to be negative pi over 2. Now with that, we have to take a look at the information that we actually have here. Okay, so there's a few things that we need to recall. We need to recall when we did e to the I theta, and that was very similar to cosine of theta plus I sine of theta, which again allowed us to make the equation, or the equals, that z was equal to the magnitude of z, e to the I theta. And we used this idea to extrapolate into what we know. Okay, so first of all, I know that I have this power here of 4. So what this means is that I'm going to use that as my root, because if I were to take the square root of the z here, I would have to take it as a 4th root, which means this whole thing would be a 4th root. Okay, so here I know that my n is equal to 4, which means my k, which is equal to n minus 1, is going to be 3, but then count all the way back down to 0. So it's going to be 3, 2, 1, 0. So I have 4 of these that I have to make. So for this one, I am going to use Euler's idea, which is what we just used in the last problem, which says the magnitude of z to the 1 over n, and then e to the I times that stuff, theta plus 2k pi all over n. Okay, so we're going to use that idea. So let's go ahead and start. We're going to start at k equaling 0. So when we do that, we got to plug in our information. So here we've got the magnitude of z. Okay. So to do that says that I'm looking at 81 to the 1 over 4 e to the stuff. So we're going to have negative pi over 2 plus 2 k pi, so 2 times 0 pi. The whole thing's divided by 4. So we need to simplify our problem. So this is going to be the fourth root of 81, which we simplify down to being 3. So in other words, here you need to do the math if able. What does that mean? It means simplify. Okay, so this becomes a 3. And then we need to look. 2 times 0 times pi means all of that goes away. So that means I am left with e to the I times negative pi over 2, the whole thing is over 4. So reducing this all the way says that I have 3e to the negative pi over 8i, and that is k equals 0. Now I have to do k equals 1. So again, this is going to be, and I'm going to write this a little bit different, it's going to be the fourth root of 81. So these two are written exactly the same. Now you can see both ways. E to the I times your stuff, which this is going to be negative pi over 2 plus 2 times 1 times pi all over 4. We have to reduce, so this again becomes 3e to the I times, and we have to look at what we have here. Well, we're going to have negative pi over 2 plus 2 pi all over 4. So when we reduce that, you're going to get 3e to the 3 pi over 8i. Okay? So here you're going to combine your terms. Remember, for this case, 2 is that lowest denominator. You'll combine the top and use your fraction rule to get rid of this denominator here. We're going to do the same process for k equals 2. So again, this is going to be that fourth root of 81. E to the I times your stuff. So negative pi over 2 plus 2 times 2 pi all over 4. We're going to reduce this down to 3e to the I times negative pi over 2 plus 4 pi all over 4 is going to end up being 3e to the 7 pi over 8i. Last here I have k equals 3. So again, fourth root of 81, e to the I times negative pi over 2 plus 2 times 3 pi all over 4. This is going to reduce to 3 e to the I times negative pi over 2 plus 6 pi all over 4, which is going to equal 3e to the 11 pi over 8i. Now, this could continue because if you look, you don't even have to do all this middle stuff. Once you do it twice, you can recognize a pattern. If you look here, I have 3e to the negative pi over 8i. My next one down, so going up by one step, I now have 3e to the 3 pi over 8. If you look here, That's a difference of essentially 4. Come to here. 3e to the 7 pi over 8i. Again, from the previous one, I've added 4. Come to the next one. I've added another 4. So if we were to guesstimate at what would happen if we tried to keep going, we've got a little bit of a pattern going on. Okay? So it depends on what your root is going to depend on how many of these you have to do. Remember that k value is just simply n minus 1. So there are 2 examples for you here on roots of complex numbers. If you have any questions, let me know. Otherwise, good luck, have fun, and I'll see you next time.